Today, we're going to pull back the curtain on the atom, and we're going to find a hidden variable, a tiny little difference that lets an element have multiple secret identities. And believe it or not, this secret explains everything from nuclear power to how we date ancient history. So let's jump right in.
Okay, just look at this. On one side, you've got lithium, and on the other, you've got carbon. They look different, they act different, their atoms are clearly built differently. But what's the one single thing that makes an atom of lithium, well, lithium, and an atom of carbon, carbon?
To answer that, we've got to start with the absolute fundamentals. Think of this part as figuring out the official ID card for any given element.
So every single atom is made of three key players, right? You've got the center, the nucleus, where you find positively charged protons and neutrons, which have no charge. And then you've got these tiny negatively charged electrons just zipping around the outside. Pretty straightforward. But here's the thing. Of all those particles, there is only one, just one, whose count is totally non-negotiable. The one number that an element absolutely cannot change without becoming a completely different element is the atomic number. That's it. It's that simple. The number of protons in the nucleus is literally an element's unchangeable fingerprint. It is what makes it unique in the entire universe. So this is the crucial takeaway. If you find an atom, any atom, and it has 6 protons, it is carbon. It doesn't matter what else is going on, that's the rule. If it has 3 protons, it is lithium. Period. No exceptions.
Okay, so we have that rule locked in, but this is where the story gets really interesting. Once that fundamental rule is set in stone, there's this fascinating twist, a kind of hidden variable that creates different versions of the very same element.
You know what? Let's use an analogy to make this easier. Think of an element, say carbon, as a car model, like a Ford Mustang. Every Mustang is a Mustang. That's its core identity. But you can get different versions, right? One with a V6 engine, another with a big V8. They are both Mustangs, but they have slightly different specs under the hood. And this brings us to the key question. If every single carbon atom on Earth must have 6 protons, does that mean every single carbon atom in the entire universe is an exact clone of every other one?
Well, the answer to that is a big, resounding no. And to understand why, we need to meet the real star of our show today, the isotope family.
And there it is, an isotope. See, the number of protons is the same. That's what keeps them in the same element family. But the number of neutrons, that particle in the nucleus with no charge, that can change. The neutron is our hidden variable.
So how do scientists keep all this straight? Well, as you can see right here with magnesium, they pack all the information into a really small space. The bottom number is the atomic number. That's the proton count, the ID card. The top number, that's the mass number, and it's the total of protons, times, and neutrons added together. And this right here illustrates the whole idea perfectly. Take a look at carbon. You have carbon-12, carbon-13, and carbon-14. They all have 6 protons, which is why they are all, without a doubt, carbon. But one has 6 neutrons, one has 7, and one has 8. They're all members of the carbon family, just different isotopes.
So how can you figure out the neutron count for yourself? It's actually super easy. It's just simple subtraction. You take the top number, the mass number, and you just subtract the bottom number, the atomic number. And whatever's left, that's your neutron count. See? Easy.
Now you might be thinking, okay, a few extra neutrons, so what? Big deal. Well, it turns out that simple difference can have absolutely massive consequences. It can be the difference between an atom that is perfectly stable and one that is powerfully radioactive.
When an isotope has an unstable mix of protons and neutrons, let's say it's a little wobbly, it becomes what we call a radioisotope. This basically means its nucleus is unhappy, it's not comfortable, and it needs to release some energy to settle down. That release of energy is what we call radiation. This table shows you exactly how that plays out. Look at magnesium or iodine. They've got both stable isotopes and radioactive ones. But then, slide over to uranium, and you'll notice something really striking. It has no stable isotopes. Every single version of uranium is radioactive.
And this instability isn't just a weird quirk of physics. It's incredibly useful. We've learned to harness it for everything. That radioisotope iodine-131, it's used to treat thyroid disorders. And the instability of uranium isotopes is what powers our nuclear energy plants. This stuff literally shapes our modern world.
So what actually happens when one of these unstable atoms decides it's just had enough?
Well, as we're about to see, this process of decay is where the number of neutrons has its most dramatic, world-changing impact. Just look at this. On the left, an unstable uranium nucleus literally spits out a chunk of itself, 2 protons and 2 neutrons, and in doing so, bam, it transforms into a completely new element, thorium. And on the right, a neutron inside a radioactive carbon nucleus actually turns into a proton, changing the atom into nitrogen. The atom is literally rewriting its own identity just to become stable.
And those little particles that are getting ejected, that's the radiation we were just talking about. They can be alpha particles, which are basically just tiny helium nuclei, or beta particles, which are super high energy electrons, or even gamma rays, which are just pure energy.
So think about that. A single uncharged particle, just one, can be the difference between the stable carbon that makes up you and me and the radioactive carbon we use to date ancient artifacts. It really makes you wonder, doesn't it? What other simple rules of science have these kinds of earth-shattering exceptions?